I am doing a recap on moments, and we said that we have three types of moments. We have raw moments. These are moments about the origin. We also have central moments, and these are moments about the arithmetic mean, and we have moments about an arbitrary point. Moments about an arbitrary point. Now, the central moments and moments about an arbitrary point are directly related, because we say the central moment or other moments about an arbitrary point, you can liken them to the assumed mean approach. So we are interested in the central moments and moments about an arbitrary point. So we can say, first of all, we let our x, or rather our deviation, be equals to x minus a, where a is the assumed mean or the arbitrary point. Then this implies that our x will be equals to d plus a, and we know that by definition the arithmetic mean using the assumed mean method is equals to a plus summation d over n, which can be written as a plus d bar. So therefore, if I'm looking for x minus x bar, the difference between the mean that is there, the observations, and the real mean, because this is what I require to compute the central moment, then this will be equals to our x, which is d plus a, minus our x bar, which is equals to a minus d bar. And you can see this one simply reduces to d minus d bar. So this is what you use for you to move from central moments to moments about an arbitrary point. So the first example is the first central moment. Central moments, we can denote them either using mu subscript r, if it is the first, r is 1, the second one, r is 2, or you can denote using m subscript r, either of the two, where your r, of course, is equals to either 1 for the first moment, then 2 the second moment, 3 the third moment, 4 the fourth moment, and so on and so forth. But in this course, we are interested to in up to the fourth moment. So if we can relate them, what we know is that if I were to calculate the first central moment, the first central moment m1 is given by summation x minus x bar raised to power 1 over n. And this one you can see will always be equals to 0. Why? Because the sum of the deviations from the mean is always equals to 0. What about the second one? The second central moment by definition is given by x minus x bar. You square these over n, which is equivalent to what? We can expand these and we can substitute our x minus x bar in terms of the deviations, the d minus d bar. So this can be equivalent to d minus d bar. You square and you divide by n. Basically what this means is we can expand this. If you expand this, you will get summation d squared using your quadratic identities, minus 2d d bar plus d bar squared. And all this, remember, you are dividing by n. Now you can distribute the summation sign, open up the brackets, and then you substitute, you make sure that you divide each of the terms by n. So we will get summation d squared over n minus 2d bar, because these two are constant, summation d over n, then plus you sum the d bar squared over n times. So this actually finally should give you our second central moment is equal to summation d squared over n minus 2d bar. Summation d over n is another d bar. So this will give you d bar squared plus this one. When you sum d bar squared n times, you get n d bar squared over n, and you can see this n and this n will cancel, and therefore you'll be left with the what? You'll be left with a d bar squared. Now these two terms are like terms, so simplifying, we get summation d squared over n minus one of them. But what is a d bar? A d bar is the mean of the deviations, which is summation d over n, and here you're supposed to do what? To square. So you can see from our previous definition of moments about an arbitrary point, which we said generally when you define, when you denote this with maybe, for example, r prime, the general one, the rth moment about an arbitrary point is given by x minus x bar, you raise to power r divided by n. But we have just discovered that this is equivalent to what? Summation d minus d